This lesson is for section 4.1 and 4.2. We're going to be solving linear systems by both substitution and elimination. Some of this will be review for you, but I want to get into defining first what a system of equations is. I think it's important for you to understand the vocabulary and know what you're trying to even find when you're solving a system. So a system of equations is just a collection of two or more equations with the same set of unknowns. Okay, so you have to have at least two unknown variables, and you have to have at least two equations. When you solve a system, all you're looking for is to find the values for each individual variable that makes the equation true for each equation. So it satisfies every single equation in the system all at once. Now, your system can be linear, meaning lines, or it can be nonlinear. So I've got two different systems here. One has a quadratic in it, and that's why you're seeing a parabola here intersecting a line. Okay? Now, what we're going to be focusing right now in this chapter are solely linear equations like this. We're going to have multivariable though, so we'll have x, y, and then later on we're going to introduce you to three variable systems. But right now we're just focusing on linear equations. Later on in a further chapter, we will start getting into quadratic systems. Now, what you're looking for is, like I said, the solution set that will satisfy both equations simultaneously. So graphically, what you're actually doing is finding the intersection, this point here, that satisfies both lines. Now, a point over here, like -5, 0, lies on this line, lies on the graph of the line, but that point does not satisfy this equation here. So the only one, of course, is the one where they cross, and that's what you're looking for. Now, I just noticed actually that this is not the graph of this particular system, because if it were the graph of this system, then I should be able to plug in the point 3, -4, which is this coordinate here, into both of these lines, and I should get a true statement. And if I try that in the top one, I end up with a false statement, which means that this point is not even on this line at all. So I apologize. I don't know how I did that, but I think your notes sheet is all going to have that exact same graph, so I apologize. It's not really good to show you an example that doesn't even relate to the graph, but I guess we're killing two birds in one stone, because you have to understand what it means to be a point on the line. That means that this coordinate here should produce a true statement if it were plugged into here and into here. And because it doesn't, it's not the solution, and it also is not on even this line here. Okay, now in the next problem, this point and this point both satisfy this particular system. So you can have actually more than one set of values for your variables as well. Okay, now let's begin by solving our system by substitution. So we're going to solve all of these systems in the beginning of this chapter algebraically without a calculator. Okay, you're going to have to know both methods that we're showing you today, and you'll be assessed on both methods. So even if you like using one method over the other, you're still going to have to make sure you practice both. So first, with substitution, what you want to do is isolate a variable. So isolate one variable in one of your equations. It doesn't matter which one you choose, but you probably want to pick values that you're going to get, I guess, smart values for. Like, for example, here, there's really no benefit in solving for either the x or the y. Here, though, in this question, if I solve for the y, I'm going to end up with two fractions as opposed to just one, so it would probably be easier for me to solve for the x. Now what I'm going to do is solve the top equation for the x variable. So I move that 3y over to the other side. Make sure you're adding it so that becomes a positive. A lot of you guys have a tendency to write that as -3y on the other side. You don't remember you're adding it to the other side, so you need to change the sign. But anyway, you're going to divide by -2 now, and you end up with x equaling -3 halves y minus 9. Now I can take this. This is now my new x. I'm using substitution. So we're going to substitute this entire expression here, this -3 halves y minus 9, and we're going to plug it back in to our other equation, so the one we did not use to solve, and we're going to plug that in for x here. Now when I do that, I have 6 times, I'm going to write this in red, -3 halves y minus 9 close that parentheses, minus 5y equals 12. Okay? Whoa, it's disappearing. I want you to notice that now you have only a single variable appearing here. So that's how you know you're doing something right, because you should be able to reduce this to a single variable equation. Now you can go ahead and just distribute and solve. So you end up with negative 9y minus 54 minus 5y equaling 12. When you simplify here, you get negative 14y equals positive 66. We're going to divide by the 14 here and simplify, so we have negative 33/7. Okay? Now, I plug that nasty looking fraction in, back in for either the y here or the y here. It doesn't really make a difference which one you choose. I'm going to do the top line again, negative 2x minus 3 times negative 33/7 equals 18, and now this is just another linear equation when I have just one variable here. I don't even need to collect like terms. I'm just going to simplify this, and again without a calculator. So you have negative 2x plus 99/7 equals 18. Subtract that 99/7 over to the other side, and then divide by that negative 2. Okay, I'm going to let you guys finish that off and check with the key. Okay, so now in problem number 2, since both variables are already solved for, I'm just going to set them equal to each other. Basically, I know that y should equal y. So 6x minus 4 should equal negative x minus 5. So now this is just a linear system in one variable, and you guys can go ahead again and solve for x. Once you figure out what x equals, you're going to take that and you will substitute that value back in for either of these two x's here to solve for the y. Okay? In problem number 3, this time there is an easier variable to solve for. So you want to be able to identify that when you're doing substitution. In this case, the x in the second line is the easier one to solve for. So I'm going to isolate the x here and add the 2y over to the other side. And now I'm going to take this and substitute it back in. Okay, now as you can see, I already substituted that back in to the other line, and I have this resulting linear equation here. Now when I combine like terms, I'm going to get a statement 12 equals 12. Now some of you might also subtract the 12 over to the other side, so you would end up with 0 equals 0. But in either case, both of these are true statements. Because these are both true statements, you are dropping the variable term. You no longer have a variable. Now this is not the same as 1y equals 0, right? That could equal, y could equal 0. But if you end up with no variable and just a true statement with your leftover constants, then this is going to be a system that has an infinite number of solutions. Okay, there are an infinite number of points that satisfy both equations. Now, graphically, that would mean that these lines are the same exact line. Okay, so how we answer this in this class? Now, you might have been able to just write infinite solutions prior to this, but in this class, what we're going to say is all points on the line, and we're going to choose one of the lines. I'm going to use this one here, x minus 2y equals 4. You do not have to put this into slope-intercept form. You're just going to choose one of the lines and say that it's all points on that particular line. So this is how we answer our variable systems when we have an infinite number of points, or if they are the same line. Because these two lines are equivalent to each other, we can just choose one of them and write on that line. Okay? Okay, I want you to notice that in problem number 4, I actually have almost the exact same linear system. The only difference here is that this is now a 6 instead of a 4. Okay, so we'd still go ahead and solve for this x in the bottom equation. And I isolate that and I get x equals 2y plus 6. Okay, now after plugging 2y plus 6 into the other linear equation, I end up with this linear equation left over here. Now, if I simplify here, I end up with 18 equals 12. Of course, you could have also subtracted the 18 first, in which case you would get 0 equals negative 6, or 6 equals 0. Those could all be statements that you would get from this equation. Now, all of these statements, though, since they have no variable term and they are not true, these are all false, that means that this system, this particular system, does not have a single point that would satisfy both of these lines at the exact same time, meaning these lines never cross. And if two lines never cross, because even in geometry you guys talked about this, these don't look like they're crossing, but at some point they will. So that means if two lines do not cross, they must be parallel to each other. So this is a system in which you have parallel lines. And what you're going to say as your answer, you're going to say, no solution, lines are parallel. So this is what we're stressing now, is to actually explain what's happening if you were to be able to graph that. Okay? So that's the recap of substitution. I didn't do this up here, but in both cases in numbers 1 and 2, since these both have a solution, a single variable solution, I stopped and had you guys solve for those. But that would mean that these two lines do actually cross and you just found the point of intersection. In number 3, we did not have a point of intersection. We had multiple points of intersection. So it was all points that are on this particular line, x minus 2y. And in number 4, it was no solution because it would be the system of two equations that, when they graph, are actually parallel to each other. Okay, next up we have elimination. Now, when we solve some systems with elimination, what we're looking for is to have, this is also called linear combination, by the way, but what we're looking for is to have the same variable on the top and on the bottom being either equivalent to each other or opposites. So in this case, since these are opposites, all I have to do is add these two lines together to drop that term out. So we're eliminating the x term here, and we end up with 6y equals negative 36. So y equals negative 6, and I can go ahead and plug that back in to either line, actually. I could have also drawn that line to here. In either case, I would be able to solve. And I get negative 4x plus 12 equals negative 12. So subtracting, I get x equals positive 6. So my solution, when I write this coordinate, is 6, negative 6, which means that these two lines do cross, and that intersection point would be 6, negative 6. Now in problem number 2, we have a system in which we do not have the exact same coefficient in front of the x or in front of the y. So there's a 1 in front of that x term here, and we can't simply just add these equations because we're not going to be able to eliminate a variable by doing so. So what we need to do is change the system by multiplying both equations or possibly just one equation in order to get the same integer coefficient. Now what I would do here is either multiply by 4 in the bottom line and leave the top line untouched, because then I can have 4x here, and then I would distribute everywhere. Make sure that you do end up distributing everywhere. A lot of people forget to distribute to that last number, in which case their system ends up giving them a crazy number or just the wrong point. So do make sure that you distribute there. I could also, though, pick the y to eliminate, and I'm going to do that here just because we just eliminated an x. So in that case, I'm going to multiply by positive 3. That way I'll have 3x minus 9y equals negative 18. So I've just rewritten this line here as a new line. They are both equivalent to each other, but I just rewrote it to make it so that I could use elimination. So I'm just going to rewrite the top line now right underneath it. You do not have to do that every time, but I like to just so that I see the variables right on top of each other. Now when I add these two lines together, this is going to eliminate the y's, and I'm left with a single variable, so x equals 9. Again, go ahead and plug that back into either of those lines and solve. I'll let you guys do that on your own. In problem 3, now I have a system in which case that I need to multiply both lines actually by two different integer coefficients so that I get to eliminate one of the variables. So I'm going to show you two different things that you could do here. If you multiply to try to get rid of the x term, you can multiply by a positive 4 in the top line and a negative 3 in the bottom line, so that you get 12x on the top and negative 12x on the bottom. So that's one way that you could do this. Now I'm choosing to pick a negative specifically so that I can just simply add those two lines together. If I were to multiply by a positive 3 and get a positive 12 here, I need to remember to subtract that whole line and then also distribute that negative everywhere. So it's a little bit trickier to do that. That's why I like to just get one positive and one negative. Okay, so do remember to do that, unless, of course, you want to subtract and make it a little bit harder on yourself. Now, I could also eliminate the y's, which is what I'm going to choose to do here. And if I want to eliminate the y's, what I'm going to do is multiply by a 4 in the top and multiply by a negative 3 in the denominator, or in the bottom. And the reason is because the least common multiple here is 24 and not 48. So I'm just, you could use 48 though and multiply by 8 and 6, but I'm just going to try to use smaller numbers and make it a little bit easier on myself. So now I distribute, and I make sure I distribute everywhere, and I get 12x minus 24y equals 48. And on the bottom equation I get negative 12x plus 24y equals negative 144. Okay, so now when I look to add these lines, this is going to cancel out. The x's are actually going to cancel out, even though I was trying to cancel out. Oh, this should be a positive, so I erase. And this is going to cancel out here, resulting in a statement that says 0 equals negative 96. Now this is false. We talked about what we were going to say when it's a false statement. So again, this would be two lines that never intersect, which means that they must be parallel to each other. So this is going to be no solution. And we're going to write specifically what happened, and that's the fact that they are parallel lines. Now in problem number 4, this is something that I'm going to be giving you guys a mini quiz on tomorrow, because I think it's important that you see a system that doesn't quite look like a linear system at first. This is a skill that you're going to be using a lot in pre-calculus and also in calculus a ton. So let me show you how to set the system up. So one of the things I notice is that this x is actually in the denominator, and so is the y. I'm going to rewrite this slightly differently. I'm going to put a 4 out in front and write that as 4 times 1 over x, because this is equivalent, right? 4 over x is the same as 4 times 1 over x, minus 3 times 1 over y equals 11. And in the bottom equation, I would have 5 times 1 over x minus 6 times 1 over y. Oh, that's supposed to be a y. Sorry, that's a typo. Change that to a y, guys. So that equals 9. All right, now what I'm going to do is, this is the, not so much tricky, but this is the skill that you're going to use a lot in pre-calculus and in calculus next year. So we're going to introduce this to you now, but we're going to use substitution here in a different way. We're going to say, let's let a equal 1 over x, and we're going to let b equal 1 over y. So we're going to use a different variable now to represent these variables here. So now by using substitution, since a is now 1 over x, now my system is 4a minus, now since 1 over y is the same as b, 3b equals 11. So that's my new linear equation now for that top line, okay? Just using substitution for what I just defined, letting a equal this and b equal that. So in the bottom equation I have 5a minus 6b equaling 9. Now this is a pretty easy system for me to solve. Now I just, it looks totally normal, and I can use elimination and multiply just the top here by a negative 2 so that I get a positive 6 here. Okay, to save some time here, what I did is I actually solved the system for you guys. And I would like you to go back and practice and make sure that you can get this also on your own, just because we have some fractions here. And tomorrow you will be getting like a little quiz, like I said, at the beginning of the year, the period, just to make sure that you know how to do a problem similar to this. So once I eliminated the b's, I got 13 thirds. I went ahead and I plugged it back into the bottom equation here, and it resulted in negative 6b equaling 27 thirds minus 65 thirds, which gave me negative 38 thirds. Now I just want to do this last part with you guys. I'm going to solve for the b here by dividing by negative 6. Now when you divide by negative 6 on the other side, that is the same as multiplying by negative 1/6. So when I do that and I multiply across in those fractions, I get negative 38 thirds, or I guess positive, you could say it's negative 18 on the bottom too, but anyhow, it's going to be a positive overall, 38/18 because I just multiply across. So this is going to simplify now to 19/9. So positive 19/9. So just to recap, I have a equaling 13 thirds and b equaling 19/9. Now what we have to do is, this technique is called substitution, because now I have to go back and remember, you defined a and b to be 1 over x and 1 over y. So now I'm going to substitute that back in. So a is now 1 over x and b is now 1 over y. So remember, we actually want to solve for x and y, not a and b, but this is going to help us by using a and b. That helped us to make it an easy, an easy linear system.
Now all I have to do is actually isolate the x. Now I could, if I wanted to, multiply by, or cross multiply here to try to isolate that x, but I also noticed that this is just a reciprocal. 1 over x is the reciprocal, or its reciprocal would be 3/13. Okay, so even if I cross multiply, I'll still get the same answer of 3/13. But now, since you have 1 over y, that would mean that y, its reciprocal, should be 9/19. Okay, so let me just re-explain that because I don't feel like I did that very well. 1 over y, if I take the reciprocal of that, that would be y over 1, right? Now if I take the reciprocal of this fraction, that would be 9/19. So this must be equivalent. So y must equal 9/19. And that's why this method works. So I get x equals 3/13 and y equals 9/19 for this variable system. Okay, that's the end of the lesson. Make sure that you either repeat that and watch it back to play it back to make sure that you can do it on your own, but you do need to make sure you can do this. All right, that's the end of the lesson. Nice job.